So basically, we are looking with respect to congestion control and quality of service. There can be a question like who exactly looks into congestion control and quality of service? Do I consider in physical layer or data link layer or network layer, transport layer? So in which layer we exactly have to consider congestion control and quality of service? That is the question. So to answer that, when I consider data link layer, we need to talk about congestion and quality of service. When I talk about network layer, we need to talk about it. When I consider transport layer also, we need to talk about it. So indirectly, what I mean to say is this congestion and quality of service, they are interlinked with data link layer, network layer, and transport layer. That is the reason, rather than considering these things in individual layers, we are trying to cover after completing all the three layers. Okay. Now, again, one more question is like, do I take care of congestion control or quality of service? Okay, which one I have to consider more important? That is the question. So the answer for that one is like, if I am improving with respect to congestion control, it indirectly improves quality of service. Okay, if we are improving quality of service, it indirectly improves congestion control. So indirectly I can say like both are interlinked. If we are ignoring one case, it means we are ignoring the other one also. Okay, clear, right?
Yes, yes.
Okay. So next we will see data traffic. Basically, when we talk about congestion control and quality of service, we are not dealing with control information or the traffic generated with control information, but we are mainly focused with respect to data traffic. Okay. So if I have to avoid this congestion, then it is nothing but we need to apply some mechanisms to control congestion. Okay. Then quality of service means we are trying to provide a suitable environment, we can say. Okay, congestion control is avoiding traffic congestion. Quality of service means we are trying to create an environment through which we will be achieving whatever the required quality of service. Okay, for example, let us say an application requires 4 Mbps data. With respect to quality of service, what we will be doing is we try to look for a path which provides us 4 Mbps bandwidth. Okay, so that is considered to be quality of service. So in quality of service, we try to create an appropriate environment for the traffic. So before talking about congestion and quality of service, we shall try to look at data traffic. Okay. So with respect to data traffic, we'll be discussing two things, uh, traffic descriptor and traffic profiles. Traffic descriptor means like how we can describe a traffic, like with respect to measurement, we can say. Traffic profiles means how traffic can vary. Okay, these are the two things we will be considering. So as you can see here, we are showing you a graph wherein x-axis represents seconds, y-axis represents data rate, and you have another other terms like maximum burst size, peak data rate, average data rate. Okay, these are some of the things which we are trying to look here. When I say average, in general, if I have let us say 10 numbers, and if we are talking about average of 10 numbers, what we will be doing is consider all sum of all the 10 numbers and try to divide with 10, basically number of values which we are considering. When we say average data rate, we are going to look for a period, let us say for 10 seconds of duration I am going to consider, and within that 10 seconds duration, how much data we are trying to send. Okay, so amount of data which we are trying to send divided by how much time we are considering the period, that will give us average data rate. So why we are talking about average data rate is this parameter will be useful whenever we try to talk about the bandwidth requirements. Okay, so we can say like an average I require 10 Mbps data rate. Okay, or on an average I am generating 10 Mbps data rate. So provide me a link or path which can provide me the bandwidth of 10 megabits. Okay, like that we can say importance of average data rate. So people also talk about like with respect to bikes and all, we talk about what is the average mileage it gives, right? Okay, so similarly average data rate we are considering, which tries to give an average what is the requirement we are going to have. Okay, then I have something called as peak data rate. Okay, in this diagram also you can see I have variation like this line basically represents complete data which we have generated over the period of time, and you can see the average requirement of the data rate is shown by this particular line. Okay, next we have peak data rate, which is like what is the maximum data rate of the traffic. So you can say like I'll be sending a data, maybe let us say here I have a point 5 Mbps, let us say. Okay, and let us say here I have a value some 11 or something. So I can say like my data rate always will lie in the middle of 5 Mbps to 11 Mbps. Okay, the range. But what is the peak value which you will be reaching? So if somebody asks what will be the temperature in summer in Hyderabad, maybe you can say like it starts somewhere around 30 and it goes till 48 49 something like that. Okay, but if somebody asks what is the peak temperature which we reach in summer in Hyderabad, then we'll be saying like 48 maybe if that is the peak value. So here also we are talking about what is the maximum data rate that you are trying to generate. Okay, so peak data rate also very important because uh, like it tries to indicate the peak bandwidth requirement of the network. Okay, next, we have something called as maximum burst size. Maximum burst size means uh, basically when we try to allocate network resources, it's okay if we try to ignore the value of peak data rate because we won't consider that as critical for the network. But we need to talk about maximum burst size. That means, for example, if we consider like the peak data rate is let us say 1 megabit per second. Okay, that is the peak data rate which a particular source is generating, let us say. And let us say normally it tries to generate at 0.5 Mbps like that. Okay, what I'm trying to say is normally average data rate is let us say 0.5 Mbps, but on some occasions you are trying to reach 1 megabit per second. That is the maximum or peak data rate which you are reaching. So if the peak data rate is just for 1 millisecond, then the network probably can handle the situation without any issue. Okay, we are saying like if I consider let us say some 120 milliseconds duration, and just for 1 millisecond I am experiencing a peak data rate, then I am not going to have any issue. Okay, I can handle that. This is something like especially during or just before mid exams you will be overloaded with subjects, right? You'll be overloaded with classes like how we are dealing now. So just for small duration if it is there, then you will be able to handle. But let us consider on all Sundays we are going to have classes. Okay, so you won't be able to take that stress, right? Even brain we need to give some scope to refresh, right? So like that you can consider peak data rate is something like very often we are trying to take these classes, or very often we are going to have this peak data rate. And if it is just for small duration, then it's fine. But if it is there like we consider 120 milliseconds duration. In that, if I say like for 60 milliseconds, I am going to have peak data rate requirement, then that is considered to be maximum burst size. Okay, maximum burst size means what is the duration for which I am going to have peak data rate. Okay, so if I consider like 60 milliseconds for which I am going to have peak data rate, then maximum burst size will be like 1 Mbps for 60 milliseconds. Understood all the three traffic descriptors?
Yes, sir.
Yes, sir.
Okay. In addition to these three, we also have something called as effective bandwidth. So effective bandwidth means basically we talk about average data rate, peak data rate, maximum burst size. But what is the effective bandwidth that network is trying to allocate for you? Okay, so that is calculated based on all the three parameters. Okay, we said peak data rate, we said maximum burst size, we said average data rate. Considering all these things, network is trying to allocate some effective bandwidth. Okay, so that is about traffic descriptor. Next, we look into traffic profiles. So basically, we have three traffic profiles: CBR, VBR, and bursty traffic. We call it as or constant bitrate, variable bitrate, and bursty traffic. When we say constant bit rate, or we can also say fixed rate, most of the times while doing experiments in CN lab, we consider these things, right? CBR and VBR. So this is one such traffic model which tries to generate data rate constantly. Okay, if I consider a particular period of time, let us say 60 milliseconds or 120 milliseconds, during that period of time, this value, whatever we are considering bitrate, it is not going to change. Okay, in this case, constant bitrate, whatever the descriptors we consider, like average data rate and peak data rate, they are going to be same. Okay, so when we consider constant bit rate, your peak data rate, okay, peak data rate and average data rate both will be same. Okay, this type of traffic is very easy for network to handle. Okay, so it's something like if we expect or if we know what will be the performance of a particular vehicle or something, we will be able to handle that without any issue. But if we have variance with respect to performance, then it will be difficult, because when we say constant bitrate, let us say 1 Mbps CBR we are generating, then obviously network can try to provide you the required resources. But if you say like I am going to have variable bitrate, what network resource the network should provide you? Because we cannot predict what can be my requirements, right? So that is the issue with variable bitrate. The rate of data flow changes with respect to time in the case of variable data rate. Okay, uh, and we try to regulate this thing. Okay, we will see how to regulate this particular case, and especially when we consider VBR, the average data rate and peak data rate, they will be different. They are not going to be same. Okay, and as we discussed, it's very easy to handle constant bitrate, but it's very difficult to handle variable bitrate. So the last traffic profile we have is bursty data. In this one, we cannot expect what kind of data we are going to get. It may be something like we can have like no transmission at all, and suddenly we can jump to something like 1 Mbps in few microseconds, and again I can come back to zero. Okay, as we are describing in this particular diagram. So initially I just started with 1 Mbps, let us say. After that I didn't have any data at all, and again suddenly at this point I'm trying to get like this. Okay, so in this case also I won't be able to provide required network resources easily, or I I won't be able to handle bursty traffic. Okay, so that is about traffic descriptors and traffic profiles. Next we have congestion. Okay, so when congestion can happen, like these things we also discussed previously. I'm just trying to repeat the same. When number of packets sent to the network are greater than what is the capacity of network we have, in that case congestion can happen. Okay, let us say the network is capable of handling 1000 packets per second, but you are trying to send 1200 packets, 1300 packets. The network cannot handle that, so congestion will happen in the network. Or the number of packets a network cannot handle, that may create congestion. Okay, so when we say congestion controlling, we are trying to talk about mechanisms and techniques that control the congestion and keep the load below capacity. Okay, so congestion control means the mechanisms and techniques which we are trying to control congestion and keep the load below the capacity. Okay, so like we discussed, like where exactly we can expect to have congestion, especially queues in the router. That is what we said, right? Okay, and this also we have seen, like when I consider offered load, that means like the load which we are generating, and good throughput or good put we are saying. Okay, so this is the capacity we are saying, capacity of the network. So what happens here is, let us say you are trying to improve your offered load, something like this. Basically what we expect to have is, after I reach capacity of the network, let us say capacity of the network is 100 packets per second. Whenever we are trying to send 100 packets per second, we expect like throughput also 100 packets per second. And the ideal case what we are trying to say here is, if I am trying to send 110 packets per second or 120, 130, 200, whatever may be the number of packets which we are trying to generate here, we expect like the minimum capacity, whatever we had 100 packets per second, that network should be able to provide. That is what we are expecting. Trying to understand, right, what I'm trying to say. So even though we cross the capacity of the network, what we are expecting from the network is, at least it should provide the minimum capacity of the network. So when I go with 200 or 400 or 500, it should be able to provide minimum capacity, that is 100 packets per second. But in general what happens is, this collapses like this, because we'll be having lot of retransmissions, because of which the network traffic will reach a point wherein the delay value will also reach infinite. Okay, but at least that is ideal, but at least we expect to have something like this desirable response, we are saying, right? At least we expect to have this one, but none of these things we will be able to reach. Okay, also we have seen, like what happens when capacity the load is increasing beyond capacity. We said like delay approaches infinity. And like with respect to this particular diagram, we are taking just like the performance uh, when we consider the case of capacity versus throughput. Once we cross the capacity, your throughput also is going to fall like anything. Okay, because your delay is going to reach infinite, and there is no way your packets will be delivered at the destination. Okay. Okay, so let us look into congestion control algorithms. So this one also we have seen, like open loop congestion control, which means like prevention of congestion before it actually happens. Then closed loop congestion control. This is something like once congestion is happened, how you are trying to regulate the traffic. Okay, regulate and control the issue. That is what we'll be discussing. And again we discussed these things, right? Congestion control mechanisms, open loop, closed loop. retransmission policy. Okay, so retransmission policy means we need to have proper retransmission policy, without which it will be very difficult to handle the things. Okay, so when you are retransmitting, okay, how often you are retransmitting, all those things come into retransmission policy, right? uh, okay, then window policy, we talked about sliding window protocol, right? Sliding window protocol, go back and protocol, selective repeat. Okay, which is the best windowing technique which I can use so that my performance, or I'll be able to use network resources without any issue. That is about window policy. And acknowledgement policy also we discussed, like how you are trying to regulate the generation of acknowledgements. In case you feel like congestion is there in the network, you just try to slow down your acknowledgement thing, so that source can also reduce the speed. Okay, then when we talk about discarding policy, if you remember, we said like whenever a router receives multiple packets, especially I can discard some of the audio transmission files, because audio is less sensitive to these packets. I don't have any issue in case if I discard audio, some of the audio files in the sense for a small duration, I am saying. But we cannot do the same thing with respect to FTP. So I need to have proper discard policy. Even though I discard some of the packets with respect to audio, it won't ask you for retransmission. But if I consider file transfer protocol, it is going to ask for retransmission. Okay, those things we need to keep in mind while we are coming up with discard policy at intermediate routers. Then next thing is admission policy. So admission policy, basically it is something linked with quality of service, we can say. So it's something like basically we are establishing connection, right? Whenever you establish connection itself, you are going to look with respect to what is the requirement I have. Okay. So while you are trying to admit the traffic, then only you are going to say if whatever the requirement can be met or not. For example, you can you can give, let us say, a path which can provide 1 megabit per second bandwidth, let us say. But if a source is requesting for 2 megabit per second, during the admission itself, you are going to deny that particular connection. Okay, you are not accepting that. So when you are not accepting that, obviously you won't have a situation wherein network needs to handle the traffic which is beyond its capacity, right? So that's what admission policy. Okay, I'll come to closed loop again. Let's go back to this particular slide and see what we are talking about. So we talk about many things here. Network provisioning, like with respect to network, we are trying to do some things. Okay, then traffic aware routing. Let's try to say like a particular path is having a lot of traffic. So by considering that, it's better routing of packets through that particular path. Okay, the path where we have congestion, it's better to avoid that particular path. Especially if we consider traffic police, they also do the same thing, right? If they feel like a particular path is completely congested, let us say during Ganesh immersion, that position, or any rally of political party, they try to divert the traffic. Okay, so basically they know like if the traffic is sent through this particular path, it will be congested and we will be in trouble, so they just provide alternate paths. Okay, that is called traffic aware routing. Admission control, we just have seen what it is. Traffic throttling, we will see traffic throttling and load shedding, what they are. uh, so basically what we are trying to tell here is, when I consider, or when I uh, see with respect to network provisioning, the prevention is very, very slow. Okay, network provisioning, traffic aware routing. So when I move from this side to this side, okay, the reaction is going to be faster. Okay, traffic throttling, you can say like we are having something like back pressure. Okay, or we are trying to send some signaling information, all those things. Load shedding means discard immediately. Okay, we are trying to reduce the load at the same point itself. Okay, so as I move from this side to the other side, the speed with which we are trying to like control the congestion is going to increase. Okay, so these are some of the approaches we have. Okay, so we discussed about this also, like back pressure, what happens. Let us say the we are trying to send from source to destination some data. At router 3, let us say I have some issue. In that case, what router 3 does is it tries to stop receiving some of the packets from router 2. Okay, so what happens in that case? Basically, source is sending to destination, but 3 is not allocating. So what happens at 2? So obviously it has to handle that situation, or else packets like congestion will happen at second router. So what it does is it tries to stop receiving some of the packets from 1. And again what it does, it tries to stop receiving some of the packets from source. Okay, stopping in the sense you can consider like I'm trying to slow down acknowledgement. Okay, previously I was receiving at 2 mbps, let us say. As soon as I see congestion, let's try to reduce it to some 1 mbps or 500 kbps. So obviously 2 has to stop, obviously 1 has to react to that. Okay, so this is what we do in back pressure. Okay, slowly we are trying to improve the performance in this case. Okay, but when I go to choke point, choke packet, uh, this router which has experienced congestion, it is going to send a choke packet to source. Previously, step by step we were doing. Okay, so the congested router immediately reporting its previous router about that, but in the case of choke packet, congested router is directly dealing with source. Okay, so which one will be faster? Which one acts fast? Back pressure or choke packet?
Choke packet, sir.
Obviously.
Choke packet.
Okay, so when we go with choke packet, we are going to have faster response, because see previously 3 has to implement, and it has to inform 2, 2 has to take decision, 1 has to take decision. Okay, lot of things. But when we consider choke packet, directly you are sending a choke packet to source. Source itself can reduce the amount of data which it is generating. Okay, then we have two examples to describe congestion control mechanisms. Congestion control, how it is done in TCP, that we have seen with respect to slow start, exponential increase, okay, and multiplicative decrease. These things we have seen. The next thing is, especially in frame relay networks. Did you study about frame relay in DSSN? Frame relay X.25? Yes or no? If you have studied, you can say yes, or else no. I'm not going to ask you explain. Okay, maybe you don't remember whether you studied or not. Okay, that's fine. So frame relay is also like a network, like your ATM networks, etc., to establish a virtual circuit from sender to receiver. Okay, so we are going to have switches here. So okay, let me show this diagram. We talked about implicit and explicit signaling here, right? When we say closed loop. So back pressure we did, choke packet we did. Implicit signaling means that is by reducing number of acknowledgements, source will come to know what is the issue with respect to the destination. Okay. But explicit signaling information means I have to send a specific message or signaling message either to the sender or receiver. For example, if I have congestion in this particular direction, okay, in opposite direction, I am going to send backward explicit congestion notification. Okay, so when sender is sending information to receiver, and in that path if I have congestion, then BECN, that is backward explicit congestion notification, we are trying to send it to sender. Okay, so here you need to understand, like whenever we consider sender to receiver, we may have several paths. It's not like only one single path which we are using for backward and forward communication, but we may be having two-way communication. Okay, two paths may be there for forward and backward communication. So the forward path, if I have some congestion, then you are going to send backward explicit congestion notification. In the reverse direction, okay, see, direction of congestion like this, and if I am sending congestion notification in opposite direction, that is backward explicit congestion notification. Okay, in forward explicit congestion notification, I have congestion, I am trying to send the information about congestion to receiver, same direction, that is nothing but forward explicit congestion notification. Okay, so in backward explicit congestion notification, sender has to deal, like maybe slowing down the rate at which it is sending. In forward error explicit congestion notification, receiver maybe it has to reduce the acknowledgements which it is generating, so that sender can slow down. Okay, so two concepts are there, and whenever there is no congestion, maybe we will have something like this. Okay, basically whenever you are sending data, within that we are going to enable one of the bit to indicate congestion notification, and we will be sending. Okay, it's just like a flag, you can say, forward error congestion notification BECN. Okay, so when there is no congestion in both directions, these things will be 0. Let us say I have congestion in the direction of A to B. That means A we need to consider as source, B we need to consider as destination. If I am sending congestion information in the of same direction of this traffic, okay, then same direction means we will be keeping FECN as 1. Okay, if congestion notification is there in backward direction, then we are saying BECN. Okay, simple thing. Your congestion notification and congestion control direction both are in same direction, then forward explicit congestion notification you will say. If they are in opposite direction, we will use backward explicit congestion notification. Okay, congestion is there in the direction B to A. So when you are sending information to A, then that is BECN, FECN, and BECN will be 0. Whenever you are trying to send notification in opposite direction, then we are saying forward explicit congestion notification flag is 0, but backward explicit congestion notification is 1. When we have congestion in both directions, then FECN in BECN both will be 1 in both directions. Okay, clear, right? Clear for everyone?
Yes,
Yes, sir.
Okay, so here we have done with